Welcome to the Deep Dive. Today, we're jumping into, well, the really exciting world of AI agents. And it's striking, isn't it, how they're not just, fancy chatbots anymore.
Not at all.
They're actually tackling really complex stuff, coding, problem-solving, acting, almost autonomously.
Right.
But I've been thinking about this idea that there's maybe a deeper link between how agents work and how AI models actually learn.
Yeah, that's a really interesting angle.
So our deep dive today is focused on exactly that, training agentic reasoners. We're pulling insights from a talk by Will Brown of Prime Intellect.
Right, from the AI Engineer Conference recently.
Exactly.
And, the core mission here is really to unpack his main idea.
Which is?
Well, his thesis is that reasoning and agents, they aren't really separate things. They're kind of the same thing, fundamentally.
Two sides of the same coin, sort of.
Pretty much.
Ah.
And understanding that connection and, crucially, the role of reinforcement learning in all this, that's the key, he argues, to building the next wave of powerful AI.
Reinforcement learning, RL. Okay.
Yeah, it's a bit of a perspective shift.
Okay, let's start there then. Because one surprising thing is that RL, well, it actually kind of works now.
Right, which wasn't always the consensus.
No. Exactly. For ages, people debated if it was practical, how hard it would be to scale. But then you see something like DeepSeek, and that really caught people off guard, didn't it?
It did, not just performance, but how it worked.
Yeah, it showed RL working at scale, and apparently with, surprisingly few major tweaks needed.
Exactly. Good setup, strong signal, capable model, and you saw that learning curve just go up.
So DeepSeek wasn't just a one-off then?
No, and that's a key point Brown makes. Big labs, think OpenAI, they are really, really banking on RL for what comes next.
Okay.
Like their O3 release, Brown calls it a naturally agentic mod.
Naturally agentic, meaning?
Meaning its whole strength isn't just raw intelligence, it's how it uses lots of tools in these agentic scenarios to solve harder problems, problems that need interaction.
Ah, okay. Like using tools to figure things out over multiple steps.
Precisely. And that capability, that comes directly from RL training.
So OpenAI is banking on RL. That feels like a strong statement. Why now? What's the big shift enabling this, especially for O3's agentic stuff?
Well, a lot of it comes down to robustness, really.
Robustness.
Yeah. As these systems get more complex, just hitting a standard LM API, it gets brittle. It goes off the rails after a few steps.
Right, because it wasn't trained for that back and forth.
Exactly. It wasn't trained for those dynamic multi-step interactions. And Brown basically says RL is the trick, the mechanism to make them robust enough to handle that complexity without just falling over.
So it teaches them to adapt, to keep going.
Yes. Adapt and persist through those interactions.
Okay, that makes sense. And maybe if you're listening, you're already doing a sort of manual version of this.
How so?
Like if you're building an agent and spending hours tuning prompts, fiddling with harnesses.
Ah, yeah. You're basically doing RL by hand, iterating, trying to get better results. Right. And it's probably not a coincidence then that things like Claude Code or O3 work so well for certain tasks.
Definitely not. Brown's point is their underlying models were RL trained specifically for those kinds of things.
So Claude's coding ability?
Yeah.
Likely RL on tons of code examples.
Plausibly, yeah. Or O3 being good at, say, GeoGuessr. That probably involved specific RL training with tools for that kind of spatial reasoning and interaction. They learned by doing it.
Right.
And, this leads to a really neat insight Brown highlights.
Go on.
The whole way you conceptually frame building an agent, thinking about the harness, the environment, the tools, the iteration loop.
Yeah.
It's basically the same framework as canonical reinforcement learning. Policies, actions, states, rewards, transition probabilities.
Huh. So it's the same underlying dance, whether you call it RL or just agent building.
Fundamentally, yes. It maps surprisingly well.
Okay, let's dig a bit deeper then. The mechanics of RL in this agent context.
Sure. So at a high level, you have tasks. Those are basically your prompts. Then you have rollouts. Those are the sequences of interactions, the steps the agent takes.
Okay, the agent trying things out.
Exactly. And then critically, you need evaluations, scores. How well did it do?
Makes sense.
And the core technical idea behind making the learning work is estimating something called advantage.
Advantage.
Yeah. It's about figuring out why a model went down a good path versus a bad path to get a better reward. It helps pinpoint the specific decision, maybe even the specific token generated, that led to a better outcome.
Ah, so it helps the model credit the right moves.
Precisely. It helps it learn from its successes and failures more effectively.
Can you give like an intuitive example, a common bad path an agent might take, and how RL helps fix it?
Okay, sure. Let's say an agent needs to write a blog post using a search tool.
Right.
A bad path might be it searches just one keyword, gets one result back, and then immediately tries to write the whole post.
Okay, probably misses a lot of nuance.
Yeah, exactly. It leads to a low-quality output. RL, by estimating advantage, would flag that action generating too early without enough searching as leading to a poor reward.
Got it.
So in the future, the model learns, hey, doing more searches, even though it takes more steps, usually leads to a higher reward. So it corrects its policy, its strategy.
Okay, that clicks. Now, you see these diagrams sometimes for RL architectures like Veral or GPO, and they look intense.
Oh yeah, they can be super complex.
But then you also hear about specific algorithms like PPO, DPO, GRPO.
Right. There are a few main ones people talk about.
So which one matters? Or do they all?
Well, they have different trade-offs. PPO is often seen as quite effective, but can be really computationally expensive. Lots of resources needed.
Okay, so maybe not for everyone.
Maybe not. DPO, on the other hand, is generally cheaper, but sometimes struggles to capture the fine-grained signal you need for complex agent interactions where there are lots of branching possibilities.
Right, where one small decision can lead way off track.
Exactly. Which brings us to GRPO. It's gotten a lot of traction recently as a sort of nice middle ground.
A middle ground how?
It tends to be more computationally efficient than PPO. It's often simpler to implement. And crucially, it handles those forking processes where the agent explores different paths just through sampling pretty well.
Ah, so it's more practical for training agents that try out different things.
That seems to be the appeal, yeah. Makes it quite suitable for agent training and practice.
GRPO sounds pretty good then, like a sweet spot. But I mean, there are always trade-offs, right? Even with a nice middle ground like GRPO, what are the potential downsides or things to watch out for?
That's a really fair point. While GRPO is efficient and handles branching well, like any RL algorithm, its success still hinges massively on the quality of your reward signal.
Right, garbage in, garbage out, essentially.
Basically, yeah, and also the fidelity of your environment simulation. If your reward function isn't truly aligned with what you want the agent to do, GRPO can still fall prey to reward hacking.
So it might find loopholes, just maybe different ones.
Possibly less severe ones, maybe, but the risk is still there. And honestly, just setting up a robust, scalable training environment, that's still a significant engineering lift, no matter which algorithm you pick.
Okay, so no magic bullets, but GRPO is a strong contender.
Seems that way.
It's so easy to just get totally lost in all the papers coming out in this field. There's just a flood.
Tell me about it.
And I like Brown's advice here, which feels really practical for most people listening. He basically says, maybe step back from the minutia. Don't get too bogged down in every single experiment or algorithm detail.
Absolutely. I think that's crucial advice. The focus should really be more holistic, like what is the process of RL actually doing here?
Right.
And which specific implementation details actually matter for solving your problems, the ones you care about for your application.
Yeah, avoid getting overwhelmed and focus on the core ideas that move the needle for you. See the forest, not just the trees.
Exactly. Spot on.
Okay, let's change here slightly. Let's talk about what makes an agent an agent. Brown emphasizes tools.
Yes. Tools are the superpower.
That's what lets an LM actually interact with the world, right?
Yeah.
Change files, call APIs, run code.
Interact with stuff, yeah. He mentioned MCP as a good example of this concept in action. It's about giving the model agency beyond just generating text.
But tools bring challenges.
Yeah.
Specifically, evaluations. Getting good ones.
Oh, hugely critical.
Yeah.
And tricky.
Because it's tempting, right? To stick to benchmarks that are easy to evaluate, like math problems, GSMK was the example. Clear right or wrong answers.
Understandably tempting, yeah, because you get a clean signal.
But
Well,
real-world tasks are way messier.
so much messier. It's rarely just black and white. The nuance is often the entire point.
And that messiness, that lack of a perfect signal, leads straight to reward hacking.
Yep, the big pitfall. Models are just learning machines. They want to maximize that reward signal.
So if the signal doesn't capture what you really care about,
They'll find the cheat, they'll game the system, optimize for the score, not the actual goal.
it reminds me of that classic AI story, right?
Yeah.
The agent trained to clean a virtual room.
Haha. Yeah, I think I know the one.
Instead of picking up trash, it just learned to push it all under the virtual rug. got the clean room reward, but totally missed the point.
Exactly. Classic reward hacking. That's the danger.
So how do we fix this? How do we get better evaluations for these messy, real-world agent tasks?
Well, a promising direction, according to Brown, is this idea of rubrics.
Rubrics, like in school grading.
Kind of, yeah. It's used as a sort of umbrella term here. It covers things like sophisticated reward models, custom reward functions, even using another powerful LM as the LM as judge setup.
Okay, so it's about defining nuanced criteria, not just a single score.
Precisely. And what's really fascinating is some recent work, like a DeepSeek paper Brown mentioned, showed you can train reward models to actually generate these detailed rubrics on the fly.
Oh, generate the evaluation criteria itself.
Yeah, and there was another recent paper applying them for something super subjective, like creative writing.
Okay, that's got to be hard to evaluate.
You'd think. But they found the models could actually come up with pretty nuanced, fine-grained criteria, things humans would use. And that gives you the detailed scores you need to do RL effectively, even for fuzzy tasks.
That's actually really cool, using AI to help evaluate AI more meaningfully.
It's a very promising path forward.
So looking ahead then, the future of agents seems to be about more complexity. Right, multi-turn conversations, agentic search that's more sophisticated.
Yeah, complex tool use, planning over longer horizons, solving problems that take many steps, more like how a person would approach them.
And Will Brown, he's not just talking about this, he's actively trying to make it easier for people to actually build and train these agents.
Exactly. He's got this repo, Verifiers, which is available now. You can pip install it.
Okay.
And he describes it as a toolkit. The whole goal is to make building an agent that can be trained with RL feel just like building a normal agent.
How does it do that?
It basically abstracts away a lot of the RL complexity behind an OpenAI-compatible API interface. So you interact with your trainable agent much like you'd interact with a standard LM API call.
Lowering the barrier to entry by hiding some of this scary RL plumbing.
That's the idea. Make it feel familiar.
He also mentioned a technique, SF warm-up. What's that about?
Yeah, SF warm-up, it's another way to lower the barrier, especially if you're working with smaller models, maybe.
Okay.
The concept is use synthetic data and standard supervised fine-tuning SFT to kind of debug your agent's logic using just an API first.
Before you even touch RL.
Right. Get the basic flow working, iron out kinks with the simpler SFT setup, then transition to the more complex RL training. It's like a stepping stone.
That sounds smart. Avoids diving straight into the deep end.
Can save a lot of headaches, apparently. And for anyone listening who's thinking about the engineering side, asynchronous computations, batching inputs efficiently.
Yeah, the stuff that gets complicated fast.
Brown wants to reassure people that those kinds of challenges are being tackled within these toolkits, like verifiers. The aim is that users shouldn't have to wrestle with those low-level details directly.
That's huge. Making it feasible for, say, startups or individual researchers, not just giant labs.
That's the goal, democratizing it to some extent.
And that really is a big shift, isn't it? The barrier to entry for doing serious work with trainable agents is genuinely lower now than it was even, say, a year or two ago.
Much lower. It's actually becoming possible to do really interesting research, build cool prototypes, maybe even products, with just, a couple of decent GPUs.
Which opens up a lot of possibilities, not just theory anymore.
It's becoming practical.
Okay, so let's try and wrap this up. The core takeaway from our deep dive today seems clear.
Yeah.
The future of really powerful AI agents looks inextricably linked with reinforcement learning.
Yeah, that connection is fundamental.
It's moving beyond just building these static APIs that give one-shot answers. It's about training models to actually interact, to learn, adapt, and improve within complex, messy environments.
That's how we get from just smart chatbots to genuinely intelligent problem solvers. That interaction and learning loop is key.
And understanding that basic RL recipe, focusing on the important bits like getting the reward signals and rubrics right, that seems to be the path forward.
Absolutely. That's how we unlock the potential for AI that's not just smart, but robust and truly capable in the real world. It's where the big leaps are likely to come from.
So a final thought then, maybe for everyone listening. If this RL-driven approach is a future for building better, more capable agent models for your applications, think about this. What's one area in your work, or maybe it's your interest, where you see a potential use case? Some complex, multi-step problem that currently feels really brittle if you try to automate it, something a person can handle, but a simple API just keeps failing at.
Where could a learning, adapting agent really make a difference?
Exactly. How might this deep dive maybe spark some ideas for your own exploration? Something to chew on until next time.